introduce our job candidate for this position here at the University of Minnesota. Ying from the Department of Geography at the Ohio State University, which we all know is the finest geography department in the world. And Ying comes highly recommended from Ohio State, and she'll be presenting her talk today, Green Accessibility and Measuring the Environmental Costs of Space-Time Prisms and Sustainable Transportation Planning. Please.
Thank you very much for the introduction. So my name is Ying, I'm a PhD candidate in the Department of Geography at the Ohio State University. Today I'm going to talk about the green accessibility, measuring the environmental cost of the space-time prism in sustainable transportation planning. And this is a research that is funded by NSF project as well as the components of my dissertation research. So to start with, what is the sustainable development? The United Nations World Commission on Environment and Development in 1987 report, Our Common Future, also known as Broadened Report, defined sustainability as the development that meets the needs of the present without compromising the ability of future generations to meet their own needs. There are three basic dimensions that constitute the sustainability. We have the environment sustainability, we need to have economic growth, progress, and we need to have the social equity as well. So what is sustainable transportation then? So the needs of, with respect to transportation is moving people and goods around. So it's a follow-up from the general definition of sustainability. The three dimensions with respect to sustainability include limit emissions and waste within the planet's ability to absorb them. We need to have economic progress that is affordable, efficient, and is balanced with other urban development. And last but not least, we also want to achieve social sustainability, and one aspect of it is to provide accessibility to individuals, to activities, services, and other peoples. So talking about accessibility, basically accessibility can be defined as the ease to participate in activities. There are three major ways to achieve accessibility. The first is to bring things together, which means if the activity locations are closer, people will need to travel less. And another thing is way to achieve it is to increase the connectivity through other means like telecommunication and remote technologies. And the third part is the most important and catch a lot of attention is the mobility. Is try to make it very easy for people to move around. Accessibility is people-based. Talking about people-based is because individual, the social economic background, the household status were going to determine their daily schedules, what they can do within the day and what kind of activities are within their daily schedule. And also the distribution of activities and services in space and what is the available time for services will going to be unique for different individuals. The third one is the resources that for individual will be also different. Some people may have iPhone, the other may not have. So, and also some people have cars, and other people may have to take the transit. So the resources for mobility and communication will be varied by individuals as well. So accessibility should be developed as people-based. The space-time prism is a key concept that in time geography that can capture the individual mobility. So it can define the potential mobility of individual given its scheduling constraints. And then given these location, origin and destination location, what is the time budget they have for the traveling and conducting activities, and those kind of stuff will limit what are the accessible locations for activities and what are the available time at those locations. The prism are sensitive accessibility measures that is people-based because it captures the individual constraints, and also it's fulfill our needs to develop individual-based accessibility measures. Usually the bigger prism are considered better. It's because bigger prism will indicate higher potential mobility, greater accessibility, so it is usually considered better. However, the bigger prism also imply greater cost, greater potential cost. The cost we're looking at here to facilitate the mobility usually will have the energy consumption, the different kinds of emission like greenhouse gas emission, noise, the safety issue, and also the public health with respect to the air quality. So the sustainable accessibility should consider both to increase the benefit and also to limit the cost. So in order to develop those green accessibility measures, the question here is it possible to measure the mobility-related cost of a prism? So our research question here is, how do we measure the mobility-related cost of space-time prisms? The objectives include develop the general theoretical framework, and then develop analytical methods and computational procedure to implement those theories, and to validate the developed measures use vehicle movement data as well as emission data. The research can not only complete the analytical time geography by depicting the interior properties of the prism, and also it can serve as the foundation to develop green accessibility measures, the benefit cost measures. The rest of the talk will be organized here. So brief introduction to what is space-time prism, what is space-time path, and what is the environment cost of the prism we're talking about. Then we're going to introduce how we're going to define the accessibility locations at time t within the prism. What is the visit probability? What is the probability to visit those kind of locations? And what is the distribution of speeds within the space-time prism? We're going to also introduce the emission cost functions and how we're going to evaluate our methods. The space-time path, basically, it describes how individuals move in space and time between those activity locations. So it is the actually mobility of individuals. If people move in space across time, it will result those kind of moving trajectories. In order to move in space, people need to trade time for moving in space. Those will result in the slope of those trajectories. And if people are conducting stationary activities, the trajectory will show as a vertical line, which means it doesn't move in space, but the individual still move in time. And the space-time prism is the envelope of all possible space-time paths. So given an origin and destination location, the total time budget to travel or conduct activities, and the minimum time required to conduct the activity, if there is any, and the maximum moving speed given the individual mobility level, those space-time prisms can be defined based on the 4 parts. And it is a representation of individuals' potential mobility. This can be understood in 2 ways. First, it is the envelope of all visible space-time paths between those 2 activity locations. And another way to understand it is it is the limit all the reachable locations in the geographic space, as well as available time at those locations. One thing we notice is that if we projecting the space-time prism to the geographic space, we have those kind of accessible locations in geographic space people can go to. And we call that area as the potential path area, which is like the area that paths can go through. For movements in the real world are usually restricted by the geometries of transportation network, as well as the properties of the network, such as speed limit, and also turning restrictions and stuff like that. The network time prism is the prism that is built upon a transportation network. As you can see on the right hand, the red part is a network space-time prism in 3 dimensions. And if we're projecting that part into the planar space, the green arcs over here means the actual locations along transportation network that people can go to. And the black area is the area that is not accessible within the time budget. I cannot go there because the time doesn't allow me. So this is a basic construction of the network time prism. So given the this kind of geometrical or descriptive introduction of the prisms, the next thing we'll try to look at is what do we mean by the cost of the prism we're looking at. There are a lot of environmental costs, but we are looking at the mobility related cost. The first thing we're looking at is the energy consumption, the fuel consumption, the stuff like that. The reason we look at it is because the transportation sector, among the other, among the 4 sectors of the oil consumption, we are going to take over 50%, over half of the oil consumption in the United States. And within the transportation sector, the light vehicle, which include cars, light trucks, and SUVs, will take over 60% of the oil consumptions. And this trend will go the increased rate of the sector as well as the light vehicle will increase faster than the other sectors and then other parts. So which means the oil consumption, the energy consumption is a huge issue in the transportation studies. And the second thing we're looking at is the emissions resulted from it. PM 2.5 is one thing that people concern a lot. On the left, it is actually a picture taken for the 2014 Beijing Marathon in China, Beijing. So you can see that people have to wear the mask when they are running because PM 2.5 is a particulate that is really dangerous to human beings. If you carry into your lungs and then your bloodstream, it will give bad health consequences. And also, it will the greenhouse gas emission is another thing we concern. Because of that, the global warming stuff will going to be one of the results. So, what the environment cost of the prism? Why do we do that? It's because usually the prism with larger volume will be considered better because it can provide greater accessibility. However, it will also imply greater cost like the oil consumption and the emission. So the cost of the space-time path is not very hard to measure because given an actual moving trajectory of an individual, and if we use something like a motor vehicle emission simulator that is already available, we can use the data along the trajectory to actually generate the cost measure, what is the actual fuel consumption along that trace. However, it is not that straightforward for space-time prism. The reason is because the prism will include all possible space-time paths. We don't know how many there will be. There might be infinite number of trajectories within the prism. And also, enumerating all those kind of possible traces is almost impossible and not reasonable and not computational. So what we're going to do is, in order to calculate that, let's look at one space-time path first. So for one space-time path, it will consist a sequence of space-time locations, which is a location with geographic coordinates as well as the time to present at that location. And when a space-time passing that location, it will have an instant speed associated with that. Given those two, we can use something like a model vehicle emission simulator, which is it's available already. So we can just use those two as the input, and the input to that software to generate what is the actual cost for that space-time path. So these are the three components we have as the components to calculate the cost. So going to the space-time prism, we still can use the cost function we use for the space-time path. The thing we need to solve is locations. There are a lot of locations within the space-time prism. So we first need to solve what is the visit probability distribution. That is, what is the probability to visit that space-time location among all the reachable locations within the space-time prism. So that is the first component. And then, given the location visit probability, the next thing we need to solve is, okay, so we have the probability to visit that space-time location. What is the speed distribution on that? So there are within the speed limit, definitely. So those are the two things we need to solve in order to calculate the entire space-time prism cost. So the methodology we're using right now will include the visit probability and speed distribution, then combine with the emission model. To start with, let's look at what are the accessible locations within the prism. So this is a prism without activity time we're looking at. So it is hard to describe it in the whole time frame, but if we give the location, start point and end point, and then slide that location at the specific time t, we can have the accessible locations at that particular time we're looking at. That accessible location extent will be determined by two things. Where we can get from origin at that time, as well as what are the locations enable me to reach to destination on time, given the rest of the time. So those two disks will give rise to all the accessible locations at that given time t. For the network time prism, we did similar things. We were going to derive the earliest arrival time at a vertex, which is a road intersection, and the latest departure time at the vertex. So there are 4 different types of movement along an edge, along a road link. So these are the 2 of them, and the other 2 will be just a symmetry of these 2. So the first one is from one vertex to its neighboring vertex. We have the speed limit that will determine the slope of it, and then we have the earliest arrival time, latest departure time at those vertices, and then that will determine the first one. And the second type is moving from a vertex, make a U-turn and back to itself. It is restricted by whether or not that link is 2 ways or 1 ways, also as well as whether the U-turn is allowed or not by that edge. So combine all this 4 different type of movement, you can see that actually the space-time prism the network time prism is a combination of all the 4 types of the movement. Like a little triangle over here and move towards the next, something like that. So this will going to give you the accessible locations at time t will be just a slice that red area with the time t. Okay, given this kind of fundamental constructions of accessible locations, we are going to model the visit probabilities. The first thing we look at is discrete time, the planar space prism, which means no network restriction. The method we use is random walk, which is for the discrete time and discrete step. So for one time step, people can move in either of the 4 directions, or it can stay to the current direction. And as time goes, that will result a binomial distribution with accessible locations as well as the probability of being that location. However, because we have a second anchor, the destination anchor, we need to go to the destination on time. This will driven us to develop our method, which is called directed random walk. That will go to capture the prism constraints to arrive at destination on time, and that will also we also develop a dynamic direction preferences. The way to understand that is the current preference to go to which direction will going to be determined by how many time I left for moving and how many distance to the destination left for me to move. If the distance is larger and time is limited, I may rush towards the destination and not go deviate from that part. So that will determine the dynamic direction preference for us to calculate the probability. This is the simulation results a sample simulation result we got. So as you can see, actually the accessible locations arise naturally. And then what we have is higher probability along the direct link the origin destination. And also notice that some of the accessible locations towards the end, theoretically, is not included. The reason is because we use discrete step space and time, and sometimes if we have to omit some of the locations at the beginning, it may result in those kind of not accessible locations towards the end. The reason is because we use discrete space and time. And then that's the reason we try to develop the continuous one to solve those kind of problems. The method we use is Brownian-Bridges. Basically, Brownian-Bridges is a theory that for the continuous time stochastic process anchored at the start and end point. So it has been widely applied to in economics to model the stock market prices, and in ecology to model the animal movements. This is the 50,000 Brownian-Bridges trajectory simulated. The original theory doesn't have the spin limit within the theory, which will result in some of the trajectory fall outside of the potential path area, as well as some of those kind of real unrealistic trajectories that is not feasible for physical movement in space. So what we do is we apply a truncated method, which apply a truncated distribution by the spatial extent of a prism at time t. The truncated distribution is a distribution that keep the fundamental properties of the original probability distribution, but we're going to restrict the domain from infinite to finite. So that is what we apply. So recall that we have the accessible locations at the specific time t. So we got the upper and lower bounds along x-axis and also y-axis. and use that to truncate the original Brownian bridge distribution during the simulation. Given that method, we will be able to simulate the distribution based on that. So these are the distribution I've selected time step from origin to destination given the time budget and the maximum speed limit. As you can see, the higher probability also along the shorter path, and it will going to have variations away from the shorter path. Okay, so that is for the planar space and time prism. Our purpose is to get the mobility-related costs like emissions and stuff like that. So we're looking at the network time prism, which is the prism to represent movement within the transportation network. In order to achieve that, the technique we use is Markov process, which is a memoryless stochastic process. The memoryless here will represent what my current status are, where I am right now. We are going to determine what I'm going to do in the future, no matter how I go here. So only the current status of the movement will determine what's going to be happen in the next time. The key concept here is the transition rate between states. So in our case, the state is the network vertices. So whether or not how I'm going to transit from one road intersection to the other intersection is basically what we are trying to model. We divided our method into two parts, two different types. The first type is non-vehicular mobility, which is loosely constrained by network, such as walking. Because like crossing the road, you need to follow stuff, but usually people can move more freely backwards along the pavement. The other one is the vehicle mobility, which will be tightly constrained by the network. Those kind of, so the car cannot just go backwards along the road when it is driving along that road sector. The two methods we use is ground motion on graph for the long vehicle mobility and the semi-Markov process for the vehicle mobility. We choose those methods according to the movement characters. For the long vehicle mobility, people can move freely within an edge, which means I can go here and then turn around and decide, okay, I'm going to go back. So individual walking, stuff like that, can achieve those kind of, belong to those type of movement. We use Brownian motion on graph, that theory, to model this movement. The movement will be will introduce a dispersion parameter to reflect the individual mobility level. So for some of the people, they can walk very fast. For others, maybe very low, or they just prefer to walk slower than others. So that will enable us to capture those kind of characters of individuals. The procedure to doing that is first, we're going to use that theory to derive the probability each edge. We're going to visit it at a certain time t. That will be determined by when is the earliest time I can reach from the origin, and when is the latest time I need to leave towards the destination. So that too will determine the probability for that edge, for that road link. And then we're going to distribute the edge probability along it. To do that, we use similar method, the truncated normal distribution. And then we're going to look at those are the accessible locations at that time t, and what are the visit probability. Okay, so let's look at what they look like after simulation. So these are walking in Manhattan. This is an example simulation result from one location to another shopping mall. It's actually there is a central station to the bus station to the central station. Let's still go from here to there. I have multiple choices. I can just directly go from there, or probably I would take a detour or do something else. So I prefer to walk in that way. So we're going to not assume any objective of how individuals are going to do that. We'll just model those kind of location probability based on the constraints imposed by the space-time prism. So at the first minute, people will leave where it starts, going towards, and the red part means high probability they will be moving towards that destination, but it's still possible for them to be somewhere else. And as time goes, as you can see, the accessible locations will be delimited based on where people can go, and also towards the end, I have some spare time to go a little further, maybe grab some snack and then go back, something like that. So this will show how the visit probability along edges going across time for the walking part. For the driving, the vehicle mobility, we cannot just move freely within the edge. Like, I cannot just turn my car around and then just go backwards freely. So what the method we use here is semi-macro process. And we're going to introduce a transition rate that reflects what kind of mobility level provided by transportation network. How easily for me to move from one location to another within that network. And the procedure to calculate it includes the calibration of the transition rate. We're going to select it several trajectories collected within one route, and then going to use the trajectory times to calibrate our transition rate. Then we're going to calculate the edge probability at that time based on how many arrival time are available and how many departure time are available, given the basic construct and then the space-time, the network time prism we have. So our example here will be driving across Manhattan. We have the vehicle movement data provided by commercial navigation vendor, which include 136,000 trajectories over a 2-week period. It is a second-by-second GPS location data, and it matched pretty well with the network data we downloaded from Esri online resources. And that network data will going to provide us with the speed limit information, the one-way restriction, as well as the turning restriction information within the network. So given the data, we create 2 scenarios. The first is driving across the southern Manhattan, so from the Holland Tunnel to Manhattan Bridge. And the second one is from the 3rd Avenue Bridge to the 59th Street Bridge. The time budget for the first one is 25 minutes, and the time budget for the second one is 40 minutes. So these are the 2 scenarios we have. So first we need to calibrate the transition rate, which will reflect the mobility level provided by transportation network. So we selected trajectories along one route. There will be one route selection, but because the time spent along that route may be different. So these are the 37 sample trajectory along a single route. People may spend from 196 minutes to even second. So this is second. Like 5 minutes to 20 minutes, 20 or even more minutes along that route. And these are the 40 sample trajectories along another route. Based on the ordinary least squares method, we can obtain the transition rate in Manhattan area of 0.003. So that is the transition rate in our study area. Given that, we're going to model, we're going to simulate the visit probability at a given time. So on the upper side is the simulated visit probability for each edge. As you can see, when they start to move, most of the time the vehicle will stay just exit the ramp and start to enter the area. And then more accessible locations, and towards the end it will go towards the destination, the Manhattan Bridge. And one thing to notice is the brown part. Although there are a lot of locations that are accessible, a lot of them have a very low visit probability, which means it's highly unlikely to visit those locations. Compared with the derived empirical distribution based on the GPS, 72 GPS trajectories, they visually have a good match. Most of the time it will follow those quicker routes, but it will still have deviations from those. It's similar to the second one, but more significant is those kind of theoretically accessible locations, but the visit probability is lower than 0.01%. So those are just visual comparison. We use the root mean square arrow to see the average differences between the simulated and the empirical visit probabilities. As you can see, the results here are showing pretty good fit. So which means our methods can simulate the probability that match the empirical probability pretty well. So that is for the visit probability. We get a good method that can match the real world data pretty well. So the next step is to have the speed distribution. We focus on the network time prism because we want to look at the mobility-related cost for the vehicles. So just a little bit recall, we have an instant speed velocity allocation at that space-time location. And for the network time, what we try to look at is the speed profile of that edge at a given time. That will be going to determine by two parts. First, we're going to have a resultant speed distribution based on arrival time and a departure time. That will give us the average speed, and combined with the maximum speed, we can derive the speed distribution. And then, given that distribution of an edge, we're going to combine that with the probability of that arrival time and the probability of that departure time to derive the entire distribution of all the possible combination of arrival time and departure time here. We're working on that one right now. And then after we have the speed distribution, the next step is to get the cost function. The physical emission model enables us to do that. It's already been developed and well actualized and validated in the transportation planning sector. And this is a physical emission model proposed by Bob in 1996. And as you can see, there are factors that are related to prism, like moving speed and location properties. What is the condition of that location, such as what is the road grade and what is the air mass density. And there are other factors that is not relevant to the space-time prism, which like the vehicle mass, engine conditions, and the gear selection. So what we try to focus on is the vehicle-specific emission. So what I mean is, we're going to apply a motor vehicle emission simulator. The input here is the edge speed profile. What is the speed distribution of the edge? And then we are going to look at just the one vehicle type. Say, okay, this is the two-door sedan I'm looking at, and given that we can have the engine type and vehicle mass and parameters that is not relevant to the prism. Using that the input, the emission simulator can do the calculation and simulation and then give us the the estimated fuel consumption for that vehicle at that specific time. And also the emission of our selection, like greenhouse gas, at that time. So the input here related to the emission is edge speed profile as well as the visible probability of that edge. How to evaluate our methods? We will going to use the primary. This is a really cool device over here. So it's called I2D, which will contain 3 different parts. The OBD receiver, which you can plug in any vehicle that is produced after 1990. 2000. Thank you. 2000. So you just plug it into a vehicle, and it will go to monitor and connect to your energy consumption data. And that data will go to transmit to this data collector and sender, and send to the satellite, and then in their database. The GPS over here will going to help us to monitor the locations, the altitude, and also the moving speed of that vehicle at that specific time, the instant speed and location. And those data will also transform to the data collector and send to their data warehouse. So these devices enable us to collect the data along the custom routes in Phoenix, Arizona. We are doing the route design right now in order to capture the visit probabilities within the network time prism. And given those data collected, we can calculate the environment cost based on our theory and methods, and then compare it with connected data and see how they match with each other. We also have the secondary data provided by North Carolina State University. And this 300 hours second-by-second GPS data has the speed profile and fuel uses and the emission rate along those routes. So using this data, what we can do is we're going to restrict our movement within those routes and calculate the environment cost and compare with the simulated one. So this is the secondary data we can use. Okay, in conclusion, mobility is good. It can provide accessibility to services, activities, opportunities, and people. And it's not that good because it will require resources consumption. It will result in greenhouse gas emission and have the air quality issue and public health concern. The space-time prism is the one that can capture the potential mobility of individuals and can be used to develop people-based accessibility mobility measures that capture the individual schedule and location constraints. The sustainable, in order to achieve the sustainability, we should represent good and bad aspects of mobility introduced by the space-time prism. The environmental cost of the prism we're looking at, such as energy consumption and emissions, were going to be estimated, measured through the way of 3 components. The first one is the probability to visit locations, reachable locations. And the second is what is the velocity distribution at the space-time locations. Then we combine with the physical emission model to estimate the cost. The significance of our research will complete the analytical time geography by exploring the interior property of the prism, and also can serve as the foundation to develop cost-benefit measures. There are 3 directions currently I have for future research agenda. The first one is we can, based on the interior properties of the space-time prism, we can refine the currently existing prism-based assessment measures to introduce the movement probabilities and then combine with the distribution of opportunity, activity, and people in space and time. and develop accessibility measures that is prism-based and probabilistic-based. The second direction is we can combine the individual movement model with the air quality exposure models, and then look at the relationship between transportation and public health outcomes. The third direction is we can employ those methods, modify it, considering the characters of animal movement, and then looking at the animal movement ecology. The data for that is already available. It's called MoveBank, which is a free online database of animal tracking data. So these are the three parts, three current ideas for the future research. Thank you very much. 5 minutes, like 3 minutes.
Questions?
Questions, comments?
Come on, be tough. It's an interview.
Yes.
I'll start with a question pretending like I'm an audience member, and then I have other little comments that I can do. I'm curious, you keep talking about we, us, we, so clearly this is maybe part of a larger research project or research group, so maybe you could talk about that. It was unclear. You never mentioned a research group, and it's unclear what your research is versus the research of the group as a whole.
Oh, thank you very much for bringing that out. It's actually, this research is funded by the NSO project. There are 3 investigators in the research. One is Professor Harry Miller from the Ohio State University, my advisor. And the other 2 is Professor Joe from the Arizona State University, who is the transportation engineer. And the third one is the one from University of Utah, who is actually a transportation planner, like political part. So my duty in this project is basically more develop the theoretical stuff and theoretical computational and analytical methods, and also collaborate with the engineer, the Professor Joe from ASU, to develop those kind of toolkits. So I have to say that more theories and analytical methods in this project is constitute my research and that project as well. And English, yeah, thank you. Mm-hmm. And I do have the comments and suggestions from the political planners, because they have more experience in the actual planner part. Yes.
So when you spoke about the ongoing project in Arizona with car movement, that sounded to me like future research, but is that part of your dissertation?
Yeah, it is part of my dissertation. We already have a framework of how it will going to integrate the tool with my methods. The data collection, we are waiting for the devices to deliver to that part, but the data collection will going to be happening on mid-November.
Okay, I would mention that because it isn't clear the timeline for that project.
Thank you.
So, so if they're wanting you to start next fall, it's like, oh, well, will she be done or not?
Thank you very much.
Yeah.
That's a good suggestion. Yes?
So, you're using Brownian bridges and random walks. This involves people, so why aren't you using a spatial behavioral model?
That's a really good question. There are a huge amount of behavioral model existing, and they are very complex and computationally expensive. The intuition here for us, this project, is to develop a simple, efficient, computational, non-expensive methods to capture the individual characters, like their space-time constraints, but do not look at how they actually react to those kind of vectors, but try to model the potential given the physical constraints of the movement. So it's a physical model instead of a behavior model. Does that make sense?
You might want to add that, but it can be calibrated to actual data.
Okay.
Yeah, that's all.
Any other comments?
I have a few comments. I typed some notes, so I'll send you some details.
Thank you.
But let's suppose that somebody in the audience is, say, from stats or statistics and really likes the model and has some detailed, specific comments. You developed this work, so I would stress you, not we, because some of this is your own work. But be ready to maybe talk a little bit technically, but also to make it intuitive, a bit more intuitive even than you did. So I'm a little bit concerned about your over-reliance on probability. The fact is that if I'm traveling across Manhattan, there's a chance I can do all these things for sure. There's some space in which I could do things. But am I going to? And if I did one of them, does that not cut out all the other options? So it's a conditional probability. Conditional that you've done nothing except straight line. There's a remaining space. Then as you get closer and closer to your end target, your options are basically running out. So your time space prisoners. So could you talk about, how much do you know about, do people wander around? Do they deviate from a minimum path? What's the real, I guess the behavior is the interesting question.
I think your question is a little bit relevant to what Harvey
Yeah.
is asking.
We're on the same page.
So you are talking about the current decision we're going to determine what people are going to do next.
I think so, yeah.
They can do next. So in response to that, you can view that as a combination of all possible decisions. So, for instance, if you're looking at this one, the higher probability is over here.
Yeah.
If I go into that location, that means I have more options in the future, right? If I go along the shorter one at the beginning, I may have more options in the future. That will result for that. So if I am currently at that location, it will have a resulted distribution in the future in the next step. And if I have I was at the yellow part, I have another distribution. And if I have the green part, I have another distribution which are different from each other.
Okay, but I think my question is probably even more simple.
Okay.
Is the 1, 3, 5, and 20, are they moments during your trip? Or are you giving me a 1-minute budget or a 3-minute budget or a 5-minute budget?
Oh, I got the question right now. Yes, it's not a time budget over here. It's the instant.
The 20-minute time mark in my journey.
It's the 20th minute out of 25
Okay.
minutes.
So if I'm at the 20-minute mark, what I can do is limited by how much of my time. I guess not. If I get to the 20-minute mark, then I'm looking forward. It's kind of memoryless at that stage, right?
Yes.
Okay. Do you know if people, as I say, wander about? Do they deviate from their path?
They do. See that part?
Yeah.
This is the 20th minute.
Yeah.
Although most of the trajectory are follow the shortest path,
Yeah.
but still there are people that possibly they make a wrong turn, or because of the traffic they cannot turn back to the right
I
way.
think you should emphasize that there's a difference between sort of theory and observation here.
Okay.
I didn't get that.
I can do that.
Or
So
just say it, yeah.
so like that one is the same. Although it follows the shorter path, but there are people there are many different factors
Sure.
like take the wrong turn, one-way restriction they don't know about and stuff like that. So they have going to one that is very far away. And it's the same thing over here. Yeah, like that. They even go. I have the same experience because I'm not familiar with the
But
road.
that suggests you deviated sort of by chance or by accident, not purposefully to do something.
We don't want to capture that part. That's the key point. We don't want to capture whether or not it's objective, or it's by accident, or do that on purpose. We just try to capture the potential here. So the only constraints, the only factors we're looking at is the spatial temporal constraints.
See, I think what you're talking now, people will like that you're animated and you're persuasive about what you're saying. Before it sounded a little bit like mechanical. So that would be a good thing to try to inject into your talk.
Thank you. I will add that to my talk. Any other?
I have some question.
Uh-huh.
I want to make sure your research target is a single vehicle or a group of vehicles, is a traffic flow or a single vehicle.
A single vehicle,
A single
individual.
Okay. I think that research is for yesterday or for tomorrow.
That's a really good question. So I think for both.
For both.
Yeah. First, we can use the past data sets to have a look at what happened in the past, like what is the visible mobility of locations, and also use that to calibrate what is the mobility level of the network, and also to look at what is the current cost of the prism. And then in the future, what we can do is scenario planning part. So if I want to build a road, I will going to change the structure of this network, right? So we can have two different plans. Given those two different plans, we can generate different environment outcomes based on those two plans. Looking at how many accessibility it increased and how many costs it introduced, how many more costs it introduced, and try to see which plan is better with respect to cost and benefits. So both past and future, I think it will be used.
Okay, so at this moment, what you have done is mainly to try to do the visit probability.
Yes.
Visit possibility, that is your work. So I think there are a lot of theoretical or medical things, and I think all this maybe they want to know how good is your method, and that means how to validate your method. So I think you have mentioned that, yes, you said the two pictures are visually matched very good, but for me, I do not understand very well, because the visit probability or possibility is an area like a lower possibility or higher something. It's an area, but the ground truth is a trajectory, it's a line. So how to match, how to compare to area and the line to
That is a good question. So here actually, you can consider that is the edge probability. So the analysis unit we have is a road link between road intersection. So the environment cost, the visit probability, the velocity profile, and the cost will be edge-based. So we're looking at what is the visit probability, what is the distribution level, everything along the edge level. And as for the comparison, quantitatively comparison over here, I should include a slide in the appendix as well on how to calculate it. So the comparison over here is also based on an edge. So we look at the edge level. So the edge was defined as the road link between two road intersections, because for vehicle movement it makes sense, right? For the trajectory, as you mentioned, like I mentioned before, we are not looking at one single trajectory. We're looking at all possible trajectories. So you can consider that as a resulted cost or resulted probability caused by all possible trajectories. So because people may change their mind, or because of various conditions, the trajectories were going to be changed over time. So we're not looking at a specific trace at this point.
Yeah. But anyway, it will not be a random. So we can change, but it's not a random. So you said random walk or directed random walk. Yeah. Maybe my question is also similar to okay. People is not animals, so they do not random walk.
I agree with that, but I remember read a paper about how people behave. Although if you look at a small amount of time, people do have those kind of behavior rules and stuff, but they also have a pattern, like how many times between two activities they do will follow like heavy tail distribution. This is similar to what we have here as actually what we generate for the semi-Markov chain includes the rate to move from one location to another. And that we can use other distribution as well, like heavy tail distribution to describe that. So that part will going to capture what you mentioned about variance in individual behavior.
Okay. One small question. It's for sustainable transportation for vehicle. So
Yes.
why did you mention the human being walk? You mean randomly walk?
That is a good question. Like I mentioned in the future research agenda, we're not limited to this project.
Okay.
The resulted theory and methods in this project, the reason I include planar space is because it can be used to animal ecology and also the public health concern. So if I have people walking on the street and combined with the air quality model, we can estimate, okay, what is the actually intake of those kind of bad stuff, and try to estimate what is the impact if they choose this route or that route.
Okay.
So that's the reason we include the planar space, that stuff, and run different type.
Thank you.
Thank you. Any other comments?
I just have one. So the lambda parameter
Uh-huh.
for the visit probabilities, that's Manhattan-based.
Yes.
So to apply this model to other cities, you would have to recollect GPS trajectories and calibrate your model.
That's a very good question. One way is use GPS data to collect that model. The other way is we do have those kind of traffic flow, travel time data that collected by DOT or some other transportation department. We can also use that part to see what is the average travel time between vertices, and use that to calibrate the number.
Yes, I think I have also answered the same question. I mean, for the velocity physics probability, I just want to ask what exact distribution you have used, or you just use like a previous samples to simulate that. I mean,
That's a really good question. For the random walk, we have the binomial distribution, and then the continuous one, the Brownian bridges, is the varied normal distribution, and then we truncated it. And for the Markov chain, we use the exponential distribution, which is the traditional way they do the Markov process modeling, the exponential distribution. I do have the formula over here, which, so for the Brownian bridges, we have the truncated normal distribution, and for the Markov process, we have the jump rate, holding time, and state probability based on the exponential distribution. So those are for different methods, we use different distribution to derive.
so some of the parameters you have already know is based on like experimental samples you have made to decide the parameters.
Yes, like the Markov chain one, the dispersion, the transition rate over here is calibrated to use the GPS trajectories. And for the the truncated normal distribution, at this point we do not use movement data to validate it, but if you have it, we can modify the variance over here, use the empirical data.
Okay.
So the variance over here will represent the mobility, the dispersion parameter over here.
One more question.
Yes.
Can you back to the pictures? I mean, the basic probability of
The network or the planar?
the network.
Okay. This one?
Yeah. So for these four pictures about this, I mean, it seems to me like the distribution is based on like you should have that bit distribution based on a certain like a base. I mean, start point or something. So for example, for the above four pictures, does your base, I mean the points, slowly move with the time passing by, or just still based on the start point?
If you are asking the lowest visibility and highest probability, or are you looking for, what do you mean by base?
I mean, for example, for this picture, what's the start point? Where is the destination?
The destination is over here, the 100 tunnel. The destination and the origin doesn't change. So this is still the origin, that is still the destination.
Okay, so for the 20 minutes, I mean, you have only 5 minutes left, but why there's still high probability around like a start point on that?
Because believe or not, based on our calculation is based on the speed limit. So the speed limit is 45 miles per hour. Believe or not, those are the locations that people can go to, like 5 minutes, they can still go there.
Okay.
Why are you
I don't think people backtrack.
Yeah, they don't, but it is possible. Like, those are only 72 traces and people are already awake. And the base for this simulation is like almost infinity number.
You could take alternative routes besides the shortest path.
Yeah.
We don't know why people do that.
We just say
You just know there's
in-
probability distribution.
Compared to the higher, those are lower probability but still possible. So something like that.
There are a lot of intersections, so do you need to consider traffic signal?
We do have turning cost.
Turning cost.
Yeah. Turning right turn, left turn, and U-turn cost associated with the moving.
Okay, did you make it with ArcMap?
I do use ArcMap to do the calculation for from one location to the other locations.
Thank you.
Yes.
I just have a general question in case there are a lot of human geographers in the department. May I ask you, well, as for me, do you think the people will be different about their behaviors when they move? Like, does a female move different, or male or children move different?
That's a really good question.
Or do you want to kind of integrate this possibility in your model in the future?
That's a really good question. So currently what we do is just to capture the mobility level imposed by the transportation network, which is subject. So we can incorporate the actual differences in individuals' responses to those constraints. Like if I have 15 minutes, I may rush towards the destination. But some people have those kind of moods that they just take time and they are not afraid to be late. So those kind of parameters can be incorporated into the model, but not at this point. We do not include any subject points at this point, but it is possible.
Okay, so that might be a future kind of a collaboration with you and other community developers. And another question in my mind is, you mentioned the computational expensive stuff. So to what degree do you think your model is expensive in computation? And I mean, especially when everybody now talking about big data and how big your model can proceed on content.
That's also. So our model doesn't use the data when doing the simulation. It's like a pre-process part. We have the pre-process part to derive the transition rate, and then that rate, we're going to use that rate to do the simulation. But when we do the simulation, it's really quick, because that one doesn't use those kind of large amounts of data. And for this kind of result that I have to generate it, it's just take about 2 minutes for the series of data that I use.
Well, as far as I know, there are a couple of computer science they're doing this complicated job using multiple agents, multiple terminals, like using the parallel computing? Do you think your model can fit in this parallel phenomenon?
If the network is really huge, I can do that, but at this point, I don't think we have to do it because the computation over here is really, it's not expensive at all. So if the transportation system we're looking at is really huge, if we look at the interregional movement.
So how huge? Do you think?
I haven't done that yet, but one reason we propose this method is because it's very inexpensive computationally.
Okay, well,
Thank you very much.